Welcome back to the Dargslan series, part 12, and this is where things get serious. Last time we generated embeddings, but a Python list falls over the moment you cross a few thousand vectors. So today we're spinning up a real vector database in Docker, comparing Chroma and Qdrant, and looking at how proper indexing gets you sub-millisecond similarity search across 1 million embeddings, all running locally on your machine. So let's be concrete about why that list breaks. At 10,000 documents, a linear cosine scan already takes around 50 milliseconds per query. Push that to 1 million and you're waiting 5 seconds, which is an eternity when users bail after 2. Memory's the next wall. 1,768-dimensional float vectors is roughly 3 gigabytes sitting in RAM, and that's before metadata. Then there's persistence. Kill the Python process and you re-embed for hours. And you've got no way to filter by things like date or category without touching every single entry. So a vector database tackles those 4 problems with 3 core jobs. First, it stores the embedding alongside the original text and any tags you care about, date, source, author, so the vector isn't floating around disconnected from its context. Second, it builds a real index, usually HNSW or IVF, which clusters similar vectors into buckets so queries land in milliseconds instead of grinding through every row. And third, it lets you filter and search in one shot. Give me the top 5 matches, but only from invoices dated after 2024. Anything calling itself a vector DB does at least these 3. Now, which database? There are 5 reasonable choices for self-hosting, and the right pick depends mostly on scale and what's already in your stack. For this series, we're going with 2, Chroma, because it's pure Python and perfect for tutorials under 1 million vectors, and Qdrant when we need real throughput and GPU acceleration. Weaviate and Milvus are powerful but heavier than we need, and PG Vector is the obvious move if you're already running Postgres. Just add the extension and you're done. Starting with Chroma, getting up and running really is one Docker command. We expose port 8000, mount a local directory for persistence so our vectors survive restarts, and pull the official Chroma DB image. A quick curl to the heartbeat endpoint confirms it's alive. You'll get back a nanosecond timestamp. Then pip install Chroma DB gives us the Python client, and we're ready to start writing code against it. And the Python side is almost anticlimactic. We point an HTTP client at our Chroma container, wire up an Ollama embedding function targeting nomic embed text on port 11434, and create a collection. From there, it's just 2 calls. col.add with raw documents and IDs, Chroma handles the embedding round trip to Ollama for us, and col.query with plain text. No manual vectorization, no cosine math, no numpy. Top K results come back ranked. Now, what comes back from query is a dictionary where every field is wrapped in an extra list. That's because you can batch multiple queries at once, so the outer list is per query. Inside, you get parallel arrays, IDs, documents, distances, and metadatas all aligned by index. Distances are what matter for ranking. Smaller means closer in vector space, so the top hit is always index 0. That's why grabbing the winner is just results documents. First query, first match. Pure semantic search gets you surprisingly far, but the moment you have docs from different sources, different years, or different users, you need structured filters too. Chroma lets you attach an arbitrary metadata dict to each document at insert time, and then at query time you pass a where clause that works a lot like a Mongo filter. The vector search runs only over rows matching that filter, so here we're asking for the top 3 FAQ entries from 2025, semantically closest to our query. In practice, this is non-negotiable for any real collection. Chroma is great for getting started, but once you're pushing past a few million vectors, or you need gRPC alongside REST, Qdrant is where I tend to land. It's written in Rust, comfortably handles 10 million vectors and beyond, and follows the exact same Docker pattern we just used. 1 container, a volume for persistence, 2 ports, 633 for HTTP and 6334 for gRPC. You also get a web dashboard out of the box at localhost -6333 which is handy for poking at collections without writing code. We'll come back to Qdrant with GPU acceleration in part 22. The Python client feels a bit more explicit than Chroma, and that's by design. You connect to the container, then create a collection where you have to declare the vector size and distance metric up front. Here, 768 dimensions with cosine similarity, matching whatever embedding model you're using. Qdrant doesn't embed for you, so you call your own embed function, then upsert points that carry an ID, the vector itself, and an arbitrary JSON payload for metadata like the source document. So which one do you actually pick? Honestly, both work fine for Ask My Docs. Reach for Chroma when you want the shortest path from script to working RAG. It's Python native, auto-embeds through Ollama, and handles 1 million vectors without breaking a sweat. Reach for Qdrant when you're going to production. The Rust core is 5 to 10 times faster at scale. You get a dashboard and gRPC out of the box, and payload filtering is first class. In this series, tutorials use Chroma. The GPU capstone later on uses Qdrant. Before you start building, let me save you a few evenings of debugging. 5 traps catch almost everyone, forgetting the volume mount so your container dies and takes every vector with it. A dimension mismatch between your collection and your embed model. Missing or duplicate IDs. Re-embedding the same documents on every run instead of hashing and skipping. And assuming filter syntax is portable between Chroma and Qdrant, it isn't, so wrap your queries in your own function and you'll thank yourself later. With the traps out of the way, here are 4 exercises to actually cement this. First, walk a code repo and index every README, then ask, how do I run this? And see if the top hit is genuinely useful. Second, feed your bash history in line by line and run semantic search on your own past commands. Third, revisit the metadata work from part 11 and watch how a filter reshapes your top K. And finally, load the same 100 documents into both Chroma and Qdrant, run the same query, and decide which one feels right in your hands. So, 5 things to carry out of this part. A Python list is fine for 10 documents, but once you're at 1 million, you need indexed nearest neighbor, metadata, and persistence. That's the whole job of a vector DB. Reach for Chroma when you want the easiest path in Python, and Qdrant when you need to scale past 1 million vectors with a real dashboard. Always mount a host volume so your embeddings survive a container restart, and always match your collections dimension to the model. 768 for Nomic, 1024 for MXBY, 384 for all mini LM. Get that last one wrong and the DB just refuses your inserts. And to make all of that muscle memory, here's the cheat sheet. 12 commands that cover 90% of what you'll actually type. The left column is Qdrant, the right is Chroma, and you'll notice the symmetry. Spin up the container, install the client, create or get a collection, add documents, query for top K, and apply a metadata filter. Screenshot this one, pin it next to your terminal, and you've got both databases at your fingertips. And that's storage online. 12 down, 12 to go. Next up, part 13 is where it all clicks. We wire the embedder, the vector database, and a local LLM into a real retrieval-augmented generation pipeline. You'll run a query against your own documents and watch the model answer with citations pulled straight from your files. See you in the next one.